Okay, good afternoon, guys. I want to start with two announcements. First, that we will have midterm. I will open this tomorrow, and it will be over break and 2 more days because some of you may not want to do this over break. So the second announcement is that last time I was incorrect that we should cancel 1 over n for impurity, because when I looked at I just used the same data in scikit-learn, and the value for impurity looks differently. So I looked at the formula, and in the formula they use the MSE, not SSR, but MSE. This line. Like it's the role in the projector. Yeah, so in the formula in Python, and I also in the paper, they use as the measure of accuracy the 1 over n also in the notes, and explain this as like MS3 doesn't depend on the number of data points. It gives the average error instead of SSR. But if we use average here, then this number, the number of points in the right node, will cancel out with no denominator. And the final formula for quality will be SSR. So I remembered SSR, but not for the impurity, but for the quality. So this is the final expression. We have this quality factor, but instead of SSR, we should use actually MSE loss. And if I'm using the average squared error here, the numerator and denominator will cancel out. And in the end, we will have this formula for quality, like sum of squared residuals in the left node plus sum of squared residuals in the right node, and factor 1 over total number of points in the parent node, which is a constant. And we can just avoid this, drop this constant, and we will get the formula for quality factor. And do you remember last time I said that we will prove that if we use as the quality factor sum of squared residuals, then the prediction in the leaf will be the average. So here is the proof. I just took the derivative with respect to prediction in left node. So 2 from the square root, from the square. And because the prediction is a constant, the sum of this constant will result in this constant multiplied by the number of terms in the sum. And if you solve this for the prediction in the left node, it will be 1 over number of the points in the left node times the sum of y's, which is exactly the mean. Now, let's think about the MAE as the impurity. So if you want to minimize the distance, so in this case, I consider two cases: the even number of points and odd number of points. So if we have points, 3 points, 0, 1, and 5, where should I choose y star such that the distances from 0 to y star, from 1 to y star, and 5 to 1 star in total will give us the smallest value. In other words, the mean absolute error will be the smallest. So where should we place y star? Of course, not outside of the range, because then the distance of these points will be greater than if we place this inside the range. But where precisely should we place? I mean, we can take the root like in SSR. That's the problem with MAE error. So to prove the result, it will take maybe entire alphabet list of class. So I just want to give you an intuition. So can we just guess what is the best position of the number y that will minimize the distances to this number? Average of all these points, the average will be 2. So if you choose 2, then the distance from 0 will be 2, from 1 will be 1, 2 plus 1, 3, and to 5, 3, so it will be 6. But can we do better? There is answer on it. Yeah, what is the median?
In the middle of the set.
Yeah, but what is 1? 1. So if you look at point 1, the distance from 0 will be 1, from 1 to 1 will be 0, and from 1 to 5 will be 4, and total sum will be 5. Okay, now let's think about even number of points. Where should we place a y star to get the smallest sum of distances from every point to this y star?
From 5 to 6.
That's correct. That's correct. Yes, because you can take 5. Oh, there is something with I draw connection. You can take 5, and the distance from 5 to 5 will be 0, and from 5 to 6 will be 1. You can choose 6. The distance from 6 to 6 will be 0, and distance from 6 to 5 will be 1. And you can choose any point in between, then the sum of these distances will be also 1. So at school, you learned that median, in case of even number of points, is the average between intermediate points. But in practice, it's actually an arbitrary point in different infinitely ends. Great. So this is just intuition that when we minimize the sum of absolute values, the best value of our target will be the median. Okay, now let's go to our today's topic, the model ensembles. How and today we will cover two approaches, voting and begging. So how to aggregate models? Let's say we have 9 different models. For example, in the first row, I used the tree of maximal depth 3 and with different number of elements in the leaves. Like in the first tree, my constraint was that in the end node, we should have at least 15 points. In the second line, the depth was 5. In the next line, there was no constraint on depth. There was constraint on the number of points in the leaves. So 15 different decision trees. And you can see that they resulted in different decision boundaries. Now I want to use the predictions from 9 models and somehow can aggregate them. I will explain later how, but if we aggregate them, this will be the resulted prediction and the decision boundary, which looks better than every individual tree. So how do you think we can make a prediction for example, for this blue square using predictions from all 9 models? So if you look at the first model, that blue square was classified as class 1, as positive. If you look at the last model, this blue square was classified as class 0. In our aggregated model, it was classified as class 1. So how do you think this classification was done based on 9 model predictions? Yes.
So take the number of models that didn't classify it as 1 compared to them to the number of models that classified it as 0.
Yes, and choose
Choose the classification that had more.
yes, more votes. And this approach is called majority voting. Like we take the prediction as the class that most models classified our point. So now let's try to apply this majority voting idea in this quiz. So in this image, you see images of RIT campus in Croatia and in Dubai. So what do you think the upper image, is it Croatia or Dubai? So raise your hands if you think that the first image is Croatia. 6, 7, and raise your hands if you think that it's Dubai. Almost none. Oh, 1. Okay. So based on your votes, we will classify the first image as the Croatia campus. And this is actually correct. You can see there is the remaining of Croatia, the trace. Okay, so next question. Now it will be multi-class classification, and number of classes will be the same as the number of countries. Which country is this fountain as symbol? Like on every postcard, maybe you will see this image. So what do you think? First, give me some ideas, some country names. Yep. Okay. First choice will be Italy. Other options? Yeah, you can speak without raising. Spain. Spain is close to Italy by language. Okay, Spain. Other options?
Greece.
Uh, any correct options? Because if we will vote without any correct option, we will get the incorrect option. Yeah. Well, okay, I will help. It's Belgium, and the name of this fountain is Mannequin Peace. So yeah, we didn't have correct answers. Let's look at the next country and its symbol. Hopefully you will guess which country. Ah,
It's in New Jersey.
okay. So one option is USA. The other option is Japan. Other options. Ah,
Eiffel Tower in Las Vegas.
well, USA we have this option. France. Okay. Who thinks that it's France? Okay, again, majority vote wins, and this is, yeah, France. Now, another question. This image was taken from Google Maps. Is it from Brussels or Paris? So who thinks that this image was taken in Brussels? Raise your hand. 1, 2, 3, 4, 5, 6, 7. Okay. Who thinks that it was taken in Paris? 1, 2, 3, 4, 5, 6. Oh, more. Okay. And it was actually taken in Paris. Again, majority vote works. Now let's think about how to use majority voting for regression task. And our target will be the number of countries in the world. How many countries in the world? So give me some numbers and we will aggregate your answers. 1, 2, what?
So do you want us to just do the
Yeah, no, not random, approximately. How do you think how many? Okay. And because it's regression, I will use as aggregation the averaging. Other options,
210.
210,
70.
170, maybe some few more. Yeah, you can speak without reason. 196, 196, and maybe one more.
172.
Okay, so we have 5 countries. Could somebody calculate the average, and I will calculate the median? One, because it's easier without calculate to calculate the median. So what is the average? Well, actually,
179.8.
thank you. Yeah, actually, the median also didn't work because it's kind of underestimation. If you look at Wikipedia list of countries according to the United Nations, some countries don't have the status of the country because like um, the territories with undecided status. So the largest country is Vatican, of course, or maybe San Marino Republic. I don't know. So, but there is no sun. Okay, I don't know. 195. So you're very close. But unfortunately, yeah, if we would have one more variant like with overestimation, then this number would be the median. Okay. So now last question on regression task before we move into the problem solving. Oops. How do oh, no? How do you think how old I am? So give me some numbers, and in this case it will be a random guess. Um, yeah, I wouldn't take points if you like. 45. Let's make some about 5 numbers. So 38. Maybe it's because here is this not very good light. Okay. Some more. Huh? I wouldn't joke. How much?
50.
50? I was expecting 15 after. Okay. So maybe one more. 82. What's your name? Okay, so could you calculate the average and I will calculate the median.
46.
Mhm. Okay, so and median it will be, so what is the smallest and the largest? I will cancel this smallest. Oh, it actually was 29 and the largest. And then I should take the average between 45 and 38. So what is the average? 2, 7, 40, 42.5. So, 40, and the correct answer is 43. So, as you remember, in case of outliers, we should use MAE because it's more stable for outliers. So this is the concrete example that MAE worked better. Okay, now we are going to do this. Wait a second. I should explain what is that bootstrap, and then we can do, because begging stands for bootstrap aggregation. And then we will do the problem. So instead of building 9 different models, we can use one model, but train this model on different subsets. For example, in this case, I used, I believe, 90% of data. So randomly choose 90% of data and train model, and you will get different decision boundaries. And as you can see, these models, they overfit the data because there are these strips, blue or orange. But if we aggregate these models, we will get pretty smooth decision boundary. So instead of training different models, we will use the same model with the same number, for example, of the depth or the number of elements in the leaves, but on different training data on subsets. And this approach is called voting on subsets. But if we will use a little bit different approach, instead of taking subsample of data, we can take the samples of the data, but with repetition. So in this case, we have 4 points, and I sampled 4 points, but with repetitions. And you can see here the point 1 repeated twice. In the second sampling with repetition, point 4 repeated twice, but we didn't have point 1. And this approach is called bootstrap. From statistics, it came from statistics. When we have, for example, when we want to estimate the mean based on samples and points, and I will use a lowercase like it's common in statistics books for points. So this is the mean expression in statistics. But can we estimate the confidence interval? Because in statistics, we're interested sometimes to get also the estimation of the accuracy of our prediction. So how to get the confidence interval for this prediction? You can get n more samples, and more samples, and you will get another estimation for the mean with new samples xi new. Then you can perform again n experiments, and you will get another estimation. And after you calculate maybe 10 or 30 estimations for mean, you can take the standard deviation of these means, and this will be your confidence interval. But what if we can't perform a new sampling? What if we just have n samples and we can't repeat the experiment, but we want to estimate the uncertainty? In this case, in statistics, this method is known as bootstrap confidence interval. So you will use the same data and data points, but you will sample from these points and points with repetition. So you will get some points I, but bootstrapped. It means that some points can repeat in your sample. Then you can perform this sampling again. You will get another estimation because you will maybe get different repeated points. And finally, you can get maybe hundreds of samples with repetition from the given n samples. And then calculate the standard deviation for this values obtained by bootstrap. And then you can get this uncertainty estimation. So we will use the same approach in machine learning when we will train the same model on subsets, but instead of using, for example, 90% of data, we will use the 100% of data. We will use endpoints, but after sampling with repetition, some points can repeat several times. And we can actually prove that the number of not repeating points, unique points after such sampling will be about 63%. How to prove that? We can calculate the probability that we didn't choose a point, like it will be 1 minus 1 over n, and calculate the probability that we never choose this point. It will be 1 minus 1 over n times. We didn't choose it on the first choice, on the second, and so on. And if you add here negative sign to the power, then you can recognize from calculus what is the limit of this expression. 1 plus infinitely small to the power of this inverse. It's e, Euler's number. So 1 over, and e is about 2.7. You calculate 1 over e, it will be about 37%. So 1 minus 37 is 60. So when you have a lot of data, you can use this approximation, and then this will give you a pretty correct number of the unique samples in this samples with repetition. So about 27% of points will repeat at least twice. Okay, now we're ready for problem solving. You have 2 problems, but we will have time only for 1 problem. So yeah, you can, yeah. We could pass the problems, but it's fine. Or maybe no, there. So yeah, and we will work with 2-dimensional features in this problem, just to illustrate how we can work with multi-dimensional features. So the first bootstrap subsamples resulted, I was working as a random number generator and generated these numbers with repetition. So twice the first data, twice the second, and so on. And for the second bootstrap, I generated this indices with repetition. So we have 3 times points with index 4, and so on. So first, let's write down these bootstrap samples. So I will repeat from my original table, I will create 2 tables. for the first and second bootstrap. Yeah, so the name came from statistics, or if you want to think differently, you can think that it came from Baron Münchhausen fairy tales, where he tried to take himself out of Mac by the uh, boot boots leash. So, the first point repeated twice. The second point repeated twice. So you can see how from one sample we can get another sample set twice. Three data point with index 3, data point with index 6, 7, 8. And the second bootstrap sample will result in point with index 2, with index 3, and 3 points with index 4. Oops. Five, six, 7. Okay, next step is to choose the feature that we will use for classification for decision rule, and it can be feature either 1 or 2. So I will create 2 data sets, one with feature 1, and I will sort by feature 1. So it will be 1, 1, 1, 1, 3, 2. Wait a second. It looks I skipped with, oh no. No, it looks correct. Okay. Yeah, it looks I skipped X3 somewhere. I should put, yeah, I looked at the next line. It should be 2, 1, 1 here. It should be 2, 1, 1. Sorry about that. So because I remember there should be also 2. And then 3, 2, 3, 2. And 5, 3, 5, 3. And finally 7, 6. If we use the second feature for split, it will be 1, 1 first. 2, 1, 2, 1. 2, 6. 3, 2, 3, 2. 4, 3, and 5, 3. So, just looking at these two tables, maybe you can understand which feature is better, just without calculating all these things. Okay, we will solve for the first bootstrap, and for the second, you will just tell me which feature is better, so we won't solve everything. So possible splits are here for the first feature. And in some papers, you will see here RL, but then I corrected, and in most papers it's correct. So if we use a correct formula for quality factor, then the formula for quality will be much simpler than we used last time, because it will be just the sum of absolute errors in the left and right node without factors. Okay, first split x1 greater than 1. Second split x1 greater than 2. Next split will be x1 greater than 3. And the last split will be x1 greater than 5. Okay, so if we use the first split, what will be the prediction in the left leaf? We use median 1. What will be the prediction in the right leaf? What is the median? 2.5, because the number of points is even. 2.5. Let's calculate the quality factor. And the quality factor is just the number of, not number, just the sum of errors. We don't have any errors for the left leaf because the prediction is exactly the same as the target. For the right, there is the difference between 1 and 2.5 will be 1.5. The difference between 2.5 and 2 is 0.5, so 0.5 twice. The difference between 3 and 2.5 also 0.5, so 0.5 4 times plus 4 times 0.5. And the difference with 4, it's 6, it's not 4, it's 6. With 6 is 3.5. So if we sum up these numbers, it will be 4 plus 2, 6. Now, let's look at the second threshold here. Again, prediction in the left node will be 1. What will be the prediction in the right node? What is the median? 3, 3, 3. And let's calculate the quality factor for the second split. Again, we don't have any errors in the left node, so 0. We have the error of 1 for 2, so it will be 1 plus 1. We don't have errors for 3, and the error for 6 will be 3. So it will be 1 plus 1 plus 3, which is 5. So this split is better than the previous one. Let's look at the third split. So if we choose the split here, then the prediction will be again 1 because it's the median. And for the right node, prediction will be 3. Let's calculate quality factor. So we have only errors with 2, so it will be 1 plus 1. And for the right node, we don't have errors for 3. We have error for 6, which is 3. And the result is the same, 5. So if we have the same quality factors, we choose randomly, arbitrary. And for the last one, the split will be by x greater than 5. The mean, what is the median here? 2. And in the right node, we had only one element, 6. And let's calculate the quality factor. We don't have errors now in the right node. So the difference between 1 and 2 is 1. So we have 1, 2, 3 errors, 1. And we have errors for 3, 1, 2. So the quality factor is the same. And we can choose arbitrary, but I will choose the split, this one, because it kind of splits into more approximately equal parts our data. So I will choose the second decision tree, decision stamp. Now let's, okay, I don't want to calculate for the second tree. Maybe you can see this region. It always will end up in one of the leaves because it has the same feature too. But the difference in the prediction will be 6 minus 4, 5 twice. So it will always, well, maybe prediction will be an average, maybe a little bit smaller than 6, but it always will be greater than 5. So I don't want to calculate, but I hope you have the intuition now that the best split will result in more similar numbers in this node. So this will be the best split. Now let's look at the second bootstrap samples. Again, sort our points by x1 feature and and x2. And again, we will choose by observation the best feature, and then we will choose the best threshold. 3, 2, 3, 2, 3, 2. Oh, this is 2. 3, 2, 5, 3, 6, 4, 7, 6. And for the second feature, 1, 1, 1, 2, 1, 2, 1, 2, 3, 2. Oh, 2, I skipped 2, 6. 2, 6. 3. Oh, yep, 3, 2, 3, 4, 4, 3. So looking at these two tables, so what do you think? Which feature will result in smaller effect? The first one or the second one? Yeah, the first one will be better because you can see in the second kind of the predictions are mixed. So like 6 is greater. Here they all go in the increasing order. And also for the same feature, we have pretty different predictions. So and for 1 and for 3, so it will increase the accuracy. So you can see by just eyeballing, you can decide actually which feature to use for split. Well, computer, of course, will go for all features and thresholds. And we have these possible splits. Can you guess, or also just looking at this table, which threshold will result in better complete?
X is greater than 3.
Yeah, it's kind of intuitive, and it's correct. So, yes, if we look at the first split, then the prediction, the median will be 2, but it will result in errors with 3, 4, and 6. If we look at this split, the prediction in the left node will be 2, and we'll get only 1 error with the first point. And the prediction below will be 4, and the error will be 1 with 3 and 2 with 6. Oh, yes, so yes, in the previous case, we had to calculate the difference between 2 and 6, which will be 4. In this case, we have 4 just for the entire quality factor. So you can see that with practice, you can just understand which split is better. Okay, so it will correspond to the decision stamp x1 greater than 3. So prediction will be 2 and 4. Now, let's calculate the prediction using these two decision stamps. So we have predictions from two models now. For example, from the first model, x1, the prediction will be 1. x3, 3 is greater than 2, prediction will be 3. 2 is not greater than 2, so prediction will be 1. For 3, prediction is 3. And for all numbers greater than 3, prediction is 3. Now let's write down predictions from the second model. x1 greater than 3. 1, 3, 2, and 3, they all will be smaller or equal than 3, so prediction will be 2. For other points greater than 3, with x1 greater than 3, predictions will be 4. And if we use the average of these numbers, the final prediction here will be 1.5, 2.5, 1.5. I'm sorry, it's a little bit glued together. 1.5. 2.5. 3.5. And for the rest of the data, it will be 3.5. So you can see that in case of one decision stem, we would have just two possible predictions. When we used bootstrap aggregation, we used the same data, but we built different decision stems and aggregated them. We get 3 different numbers in our target. So this is the idea of Bayesian. Now let's give the definition of random forest. The random forest is the Bayesian of random trees. So the only thing remains to define what is that random tree. But when we define what is the random tree, what is the random forest is just the same procedure, like build the random trees on different subsets, bootstrapped subsets of data. So okay. Okay, this is just one line. So if you look at the second page of the problem solvents, you will see that I asked to build the decision stem for the first bootstrap samples using the first feature, and for the second bootstrap using the second feature. So this is the idea of random tree. Instead of going through all possible splits for every feature, we will choose a feature randomly and try all possible thresholds only for this feature. So in this case, my random choice was 1 for the first case and 2 for the second case. So this is the idea of the random tree. In every node, instead of trying all possible features and all possible thresholds, we will use only a subset of features. For example, if we have 100 features, you can use 5 random features and only calculate thresholds for this randomly selected 5 features. It will, of course, reduce computation a lot. And this is the definition of random tree. When we choose the threshold, not for all possible features, but for a small subset of these features. Oh, the idea behind this, like using random subsets of data, using random subsets of features, is in this so-called bias variance trade-off in machine learning. We have this decomposition of error of our model into bias, variance, and noise. The noise component is out of our control. It comes from the data, with the data. But bias and variance we can reduce. So let's first talk about bias, and when we will talk about variance, then you will understand why we use this model aggregation. So first question. Here I plotted 10 different linear regressions, but they all kind of glued together, but these are different lines. In the next image, I plotted 10 different random trees of, sorry, just decision trees, sorry, not random, decision trees. So, and then use the average prediction, this purple line. What do you think, which model, well, I think, let's start with the easier question. Which model has smaller bias, smaller variance? The decision trees or linear regression? Of course, linear regression has smaller variance. What about bias? Which model kind of follows better the data? The linear function for nonlinear curve or the decision trees? Which model has lower bias? What do you think? Trees, they can follow the pattern. So this is first idea, that linear model will have a high bias for nonlinear data. Trees will follow better. And if we build, like, as you remember, a deep tree, it will approximate our data pretty good. So if you want to reduce bias in this errored formula, choose a model with smaller bias. That's why random forest is used, and later we will talk about gradient boosting, which also uses trees as base models. How to reduce the variance? The formula for variance, for the sum of the variance of the sum, variance of the sum, for example, I average the models. If I had n models and average divided by n, As you remember, the factor will go out with power 2. And if we assume that the variance of every model is approximately the same, it will be n times variance. So it's the sum of variances, but it will, if the variances are the same, it will be n times variance of one model. It doesn't matter which index I'm using, n or 1. But if our models are not independent, there will be also additional term sum over all possible indices of the covariance between AI and AJ. And if we assume, so this is the double sum, so it's approximately n squared. So that's why n squared will cancel out here, and n squared will cancel here. So if we assume that covariances are approximately the same, then we will get just covariance. So if you want, what we can observe from this expression, if covariance is 0, it means that if our models are independent, the variance will decrease when we aggregate more models. So that's why the model aggregation actually works well. With the increase in number of models, this factor will reduce the variance. So the second question, how to get independent models? And this is the answer. If you use bootstrap subsets, for example, or different subsets, you can build a model on a half of data and the same model on another half of data. So you will get independent models because you used different data. So this is the first idea, to use different subsets. It can be bootstrap as well. The second idea, to make the models very different, to use different features when we make the decision in every node of our decision tree. So that's why actually we want to use random trees. Because for one tree, you will use features maybe from the first to the fifth. In another tree, you will use features from fifth to 10th and so on. They will, the decision rule will be different for every other tree. Well, maybe some features will repeat because it's random choice, but this is the idea that if we use this randomness, it will reduce the variance. And as the result, it will reduce the total error of your model. Okay, here is the illustration how the correlation depends on the number of features we choose for the decision. If you use small number of features, let's say 5, then randomly select 5 features and go for all thresholds only for this feature. Then correlation of models built by this feature selection is small. If you use a larger number of features, then the models built in this way will be more correlated. So, and in practice, to use less features is better for computational efficiency. Okay, so this is the definition. Random forest. Oh, yeah, so, and this is actually a plot on the right of the random forest for our data. And you can see that for one part of the curve, it approximates really nicely our curve. Also, it's very stable for training. Here I used different number of decision trees, like from 1 to 1000, and this is the plot on the test data. Typically, we have overfitting. The accuracy on the test goes up with, and this is overfitting. Here we don't have overfitting, so you and also there are recommended parameters in this paper by Freeman, who also actually introduced decision trees in 1980s, 1985. He also introduced random forest and provided the number of features, how many features we should choose randomly for the decision in the node for classifications of the number of features, for regression the third of features. So it's a nice model because we don't need to tune hyperparameters. How many trees to choose? Just choose thousands. It will work. Well, maybe it will work long, but choose 100. It won't hurt. How to choose the number of features for split? This is defined in this paper. So you just may want to choose what is the depth of the trees that you want to use. And this is the illustration of the random forest. There is just one let's see.
Universal.
No. Inaccuracy, because we use the data points with repetition. In this example, it looks like we just use different subsets, but in Bayesian we use bootstrap, so some points will repeat, but not all the points will be used for every tree. So we built the trees, and these trees are randomized trees, because in the every node for decision we use a random subset of features, and as the result we will use, for example, some points to train one decision tree. And here I didn't use for points with either 3, 4, and 5. We will use other points to train another tree, but we won't use some points for fitting this tree. And there is a nice feature out of the. Let's talk about this next time. I just want to show error estimation, so you don't need to create even validation set. You can use unused points for error estimation. I just want to show you the results. So this is the decision tree for our data points from problem solving. And the threshold is 2.5. Our threshold was 2, but you remember scikit-learn uses between 2 and 3. And absolute error, you remember quality factor was 5. If we divide by the number of points, 5, we will get 1. Then in the scikit-learn, you can indicate number of trees. And for example, bootstrap true. If you don't use bootstrap true, then it will use just, for in this case, 90% of points. will choose randomly 90% of points. If you use bootstrap true, it will sample the same number of points as in your data set, but with repetitions. Okay, I think we're out of time. Let's stop here and have a great break.
So, once the-
Yeah, you can leave these papers